Assalamualaikum warahmatullahi wabarakatuh, and good afternoon. So today I'm going to discuss on chapter 6 and 7, antenna and wave propagation. So as we all know, this will be the last class in this semester because this is the last the week 14th, and next week will be the study week. So I'm going to compress these two chapters in one video recording. So let's look into the characteristic of the electromagnetic waves or EM waves. EM waves are produced by the acceleration of an electric charge. So E and H field are perpendicular to each other at all points. So if you refer to this figure here, this is the electromagnetic wave propagation in z-axis, and the component is E and H field. So we can use Fleming left-handed rules to determine the direction of propagation. The electromagnetic waves, EM waves, that travel along a transmission line from the source to the load are called incident waves, and those that travel from the load back toward the source are called reflected wave. So this basically is the incident wave propagate in z-axis. So this is the animation of the electromagnetic waves. It propagates in this direction. From here, you can see lambda. Lambda is the wavelength. So how we determine the lambda? It is basically the distance between any two corresponding points on adjacent wave. Basically, it's a complete sinusoidal wave from one corresponding point to another corresponding point. So from if we know this lambda, we can get the frequency of the electromagnetic wave by using equation C equal to F lambda. So C is the propagation of the speed of light, F is the frequency, and lambda is the wavelength of the electromagnetic wave. So this is just the proof how we can get this equation C equal to F lambda from this equation here. So we start with the distance equal to velocity times time. So from here, time, we know T is equal to 1 over F. If we substitute this equation here into this equation, we get lambda equal to V over F. So we also know that V, the velocity is in free space propagation, is the same as speed of light, which is C. So that's why you get C equal to F times lambda. So free space propagation of EM wave is often called radio frequency propagation, RF propagation. So TEM wave propagate through dielectric material including water, so not only in air. However, TEM wave do not propagate through lossy conductor, for example seawater, because the electric field causes current to flow in the material that rapidly dissipate the wave energy. So this is the category of the electromagnetic wave. So we have radio wave, infrared, ultraviolet, X-ray, and gamma ray. And we also need to know that all radio waves propagate through free space at the speed of light. So this figure shows the wavelength and the application of the electromagnetic wave. If you look at here, at radio frequency, which is AM or FM radio frequency, the wavelength in meter is 10 kilometer length. However, if it goes to the higher frequency, which is the gamma frequency, the wavelength is much smaller, very small, uh, which is 10 power of minus 12 meter. So radio waves are electromagnetic waves which consists of electric and magnetic field. The strength of a magnetic field produced around a conductor, for example, a wire antenna, is H equal to 1 over 2 pi d. H is the magnetic field and d is the distance from wire. And electric fields are produced by difference in voltage potential between two conductors. So this is the equation for the electric field, where E is the electric field, Q is the charge between conductors, epsilon here is the permittivity, and d is the distance between conductor in meter. So EM wave represent the flow of energy in the direction of propagation, the rate of which energy passes through a given surface area in free space is called power density. So this power density, we can use the equation to get this power intensity. So P equal to E RMS times H RMS. So E is the RMS electric field intensity and H is the RMS magnetic field intensity. So we also can determine the impedance of the characteristic impedance of the free space, which is 377 ohm. This value is fixed. So we use this equation to get this value. So this equation is ZC, which is the characteristic impedance of the free space, equal to square root of mu naught divided by epsilon naught. So mu naught is the permittivity of in free space, and epsilon naught is the permittivity of free space. So let's look into the inverse square law. Before that, we look into the isotropic radiator. So a true isotropic radiator does not exist. So if you look at this figure, shows a point source that radiates at a constant rate in all directions. So this is called isotropic radiator. So for example, point A and point B, here and here, are an equal distance from the source. Thus, the power density at point A and point B are basically equal. So however, it is closely approximated by an omnidirectional antenna. So for this type of radiation is not exist in real life, but we can say that it is approximately similar like omnidirectional antenna that we're going to discuss in the slides after this. So basically omnidirectional antenna is commonly used in Wi-Fi or access point in homes or school or college, because it radiates 360 degree and the power density at each point here is equal. So an isotropic radiator produces a spherical wavefront with radius of r. So all points at distance r from the source lie on the surface of the sphere and have equal power density. So at any instant, the total power radiated is uniform distributed over the total surface of the sphere. So this assumes that the lossless transmission medium. So what actually inverse square law is? It says that power density is inversely proportional to the square of the then of the distance from the source. So P here, power density here is proportionally to the distance of the source, which is R. So this is the equation that we can use to calculate the power density. So P1 is the power density, P radiate is total power radiated from the source, and R is the radius of the sphere. As waves propagate through free space, they spread out, resulting in reduction in power density, and this is called wave attenuation. So it occurs in free space and Earth atmosphere. So because the attenuation is due to spherical spreading of the wave, it is sometimes called space attenuation of the wave. So we can calculate this wave attenuation using this formula. So the P1 is the input power and P2 is the output power. So this sigma is the wave attenuation. And these two P1 and P2, the unit is in watts. And you get here is wave attenuation here is in dB. Other than attenuation, we're going to also discuss on the wave absorption. So Earth atmosphere is not a vacuum, so it contains atoms and molecules of various substances such as gas, liquid or solid. Some of this matter can absorb EM wave. So this is called absorption loss. So as EM wave propagate through Earth atmosphere, energy is transferred from the wave to the atom and molecule. So it interchange energy from free electron and ions. So if the ions do not collide with gas molecule or other ions, all energy is converted back to EM wave. But if the ion collide with other particles, they dissipate the energy that they have acquired from the EM wave, resulting in absorption of the energy. So for example, if we look at this graph here, so we are going to look into the effects of the wave propagation due to oxygen and also water vapor. So the y-axis here is the attenuation and the x-axis here is the frequency. So if we look at the oxygen first, the straight line here, we can identify that at around 60 gigahertz here, the oxygen, the absorption band due to the oxygen is really high at this frequency, and the second band is at the 140 gigahertz. So if you look at this dotted line, which is the water vapor, the first absorption band due to the water vapor is around at 22 gigahertz, and the second is at the 190 gigahertz. And if you look at this, the trend here for the water vapor, as the frequency goes higher, the attenuation is become higher. So at the top here, if you look at this point here, water vapor is at 30 dB per kilometer attenuation. So it's really high. So basically, water vapor causes significant attenuation of electromagnetic wave at above 10 gigahertz. So at lower 10 gigahertz, basically the effect or the attenuation from the material absorption is really low. Similar to the rain, at high frequency, The rain attenuation radio transmission much more severe. So at high frequency, the attenuation is become higher. So this figure basically shows the effect of rain on EM or electromagnetic wave propagation, which is starting from 3 GHz to 40 GHz frequency. So if it's heavy rain, basically the attenuation is really higher, is much higher than the light rain. Let's look into the optical properties of the radio wave or EM wave. So it has three properties. First is refraction, reflection, diffraction, and interference. So first we're going to discuss on the refraction. So refraction is the changing of direction of an EM ray or EM wave as it passes obliquely from one medium into another with different velocities of propagation. So if you look at this, in this figure shows that the medium 1 is less dense than the medium 2. So these rays have changed the direction as the interface of these two medium. So the amount of refraction depends on the refractive index of both material here. So EM wave is similar like light. So lights also refract. So same properties as the EM wave. So we can use this equation to get the refractive index, n equal to c over v. C is the speed of light and v is the speed of the wave in the given material. So for example, the material 1 is in free space, so we use the speed of light, and material 2 might be a glass, so we need to calculate or determine or obtain the speed of the wave propagate in the glass. So we also can use the Snell law rules, n1 sine theta 1 equal to n2 sine theta 2 to determine or to obtain the angle of incident or refraction and also the refractive index of both materials. So if you use this equation, you can also determine the dielectric constant or epsilon of the both medium. So let's look into the reflection. So EM wave reflection occurs when an incident wave strikes a boundary of two media, and some or all of the incident power does not enter the second material. For example, the second material or medium 2 here is metal. So all of the EM wave will be reflected back and not absorb or refract in this metal. So the wave that do not penetrate the second medium are reflected because all the reflected wave remain in medium 1. The velocities of the reflected and incident wave are equal. So basically the theta r is equal to theta I here. Diffraction is defined as redistribution of energy within a wavefront when it passes near the edge of an opaque object. It is the phenomenon that allows radio wave to propagate around corners. So for infinite wavefront, Huygens principle, which I'm going to show you in the next slide, state that every point on a given spherical wavefront can be considered as a secondary point source of EM wave from which other secondary waves are radiated outward. So let's look into this figure. If we have a source over here and it passes through a slot, so from this slot here, it produces a secondary wave because of the diffraction. Similar to if we have an obstacle over here like a wall, and there's an edge over here. So at this edge, when the electromagnetic wave hit this edge, it produces another secondary wave that propagate like a main source or main electromagnetic wave. So each secondary wave points radiate energy outward in all direction. The wave front continues in its original direction rather than spreading out, because cancellation of the secondary wave occurs in all directions except straight forward. Thus, the wave front remains plane. So if you look at this, it might be cancelled from each other if it has another secondary source over here. So lastly is the interference. So radio wave interference occurs when two or more electromagnetic waves combine in such a way that system performance is degraded. So interference is subject to principle of linear superposition of electromagnetic wave. So the principle of linear superposition states that the total voltage intensity at the given point in space is sum of individual wave vector. So if you look at the next figure in the next slide, can be seen that at point X, the two waves occupy the same area of space. However, wave B has traveled a different path than wave A. Their relative phase angle may be different. So if the difference in distance traveled in odd integral multiple of 1/2 wavelength, reinforce takes place, and if difference in distance of travel is an even integral multiple of 1/2 wavelength, it will cancel the electromagnetic wave. So this is the figure that shows the EM wave interference. So at the receiving side, X over here is receiving two components, which is the first one is the wave A, which is the line of sight component, and the second is the wave B, which is the reflection component formed predominantly by a single ground reflected wave over here. So it's reflected back to this point X here. So as you can see, the distance between wave A and wave B is different, and it might produce different phase for these two electromagnetic waves. So if the different in distance travel in odd integral multiple of 1/2 wavelength, so reinforce techniques where it will multiple the amplitude of the signal from the source here, because it produce an odd integral multiple. However, if the difference in distance travel is an even integral multiple of 1/2 wavelength, total cancellation occurs. So it might also can cancel both signal over here if the phase might be opposite to each other. So more likely the difference in distance falls somewhere between the two and partially cancel occurs. So for frequency below VHF, the relative large wavelength prevents interference from being a significant problem. However, with UHF and above frequency, micro frequency or millimeter wave frequency, wave interference can be severe. From this slide onward, we're going to discuss on antenna. So antenna is a metallic conductor system capable of radiating and capturing EM electromagnetic energy. It is used to interface transmission line to atmosphere and the atmosphere to the transmission line. So at the transmit end of a free space communication system, An antenna converts electrical energy traveling along a transmission line into EM waves that are emitted into space. At the receiver, an antenna converts EM wave in space into electrical energy on a transmission line. So if you look at this figure, this is basically antennas. So this is usually used for terrestrial television broadcasting. You connect it to your TV to get a channel, TV channel, and here it used for satellite communication. So this antenna will communicate with a satellite at the sky. And the last one is the TV terrestrial television broadcast antenna, which is outdoor antenna that we need to place on top of our roof or our house. Usually we use this if the signal is low, we cannot use this kind of antenna, so we have to place it an outdoor antenna on top of the roof. So this is the basic operation of transmit and receive antenna. So the transmitter can be modeled as a Thevenin source consisting of voltage generator over here, a series impedance which deliver transmit power to the transmit antenna. So this is the transmit antenna. So at the near field region, which is at this region here, we have a spherical wave. However, at the far field region, starting from this point here, it becomes a plane wave. So the receiving antenna will receive the plane wave electromagnetics signal. So let's look into one of the characteristics of an antenna, which is the radiation patterns. So a radiation pattern defines the variation of power radiated by an antenna as a function of the direction away from the antenna. So this power variation as a function of arrival angle is observed in the antenna far field. So basically we can generalize or categorize antenna into three types of radiation pattern. The first one is the isotropic radiation pattern, which is usually not cannot be realized in the real world or real application. However, for omnidirectional radiation pattern and directional radiation pattern, we can implement it or provide it in the real application. So omnidirectional radiation pattern has a donut shape or a toroid radiation pattern. So it looks like a donut. So in this case, along the z-axis over here, which correspond to a radiation directly overhead the antenna, there is very little power transmitted. So that's why there's a green zone over here, which has low energy intensity. However, at the rate here perpendicular to the z-axis, x and y over here, so the radiation is maximum. So that's why it shows a red pattern over this part. Similar to the directional radiation pattern. So this type of antenna have a single peak radiation in the radiation pattern, which is at the front over here. So usually the radiation pattern, the antenna with directional radiation pattern is used for point-to-point communication. So these antenna are very common. For example, a high gain directional radiation pattern include this antenna or parabolic antenna, and also a slotted waveguide antenna. So it has a very directional radiation pattern. So for omnidirectional radiation pattern, usually used for home or wireless LAN or Wi-Fi, because you want to get a 360 coverage. And depends on the radiation pattern of these two types. Omnidirectional radiation pattern can only cover a small radius. However, with directional radiation pattern, it can the radiation can go up to few kilometers or maybe few hundred kilometers because it is very directional. From the radiation pattern, we can also determine or get the front to back ratio and also front to side lobe ratio. So the front to back lobe ratio is front lobe power over back lobe power, while front to side lobe ratio is front lobe power over side lobe power. So what is side lobe? Side lobe is a lobe adjacent to front lobe, which is in 180 degrees, while back lobe is a direction exactly opposite of the front lobe. So let's look into this figure, which might be easier for you to understand. So for example, we have a directional radiation pattern where this is the main lobe. So with the opposite side of the main lobe is the back lobe, and then the other lobe at the 180 degree from the 90 degree from the main lobe is the side lobe over here and also over here. So from this equation, for example, front to back lobe ratio, so we just need to know the magnitude of the main lobe and also magnitude of the back lobe. So from there we can divide and get the front to back ratio. And the equation given is in watts. So if it's in dB, you have to deduct or minus it. Other than that, you also need to know how to calculate the near field and also the far field region. So the near field region is the field pattern that is close to the antenna. So the near field is defined as an area within a distance 2d square over lambda from the antenna over here, this one. So d is the antenna diameter and the lambda is the wavelength of the operating antenna. And similar goes to the far field. So the far field is a field pattern that is greater distance from the antenna. So it uses the same equation, but the distance r should be larger than this equation. The power that reach the far field continue to radiate outward and never return to the antenna. And the radiation pattern is important, where antenna radiation pattern are generally given for the far field. Okay, let's look into the isotropic antenna. So this kind of antenna cannot be built. It's just a theoretical assumption and it cannot be realized in the real environment. However, this is a standard that which the real antenna are compared to. So basically this is lossless, and if you look at this figure, the 0 O here is the source point with the power P watts. And the Q here is the outer layer and R is the distance. So for the power density, you can use this equation over here, which is the inverse square law that we already discussed in the previous slide. So power density is equal to P, which is the power of the source over here, O, divided by 4 pi R square. And the unit is watt per meter square. And from this equation, we can also find the electric field intensity, which using this equation, which is square root 30 times P over R. So the inverse square law basically is a power density is inversely proportional to the square of the radius R of a sphere. Okay, let's look into a few types of antennas. There are wire antennas, aperture antennas, microsweep antennas, array antennas, reflectors antennas, and lens antennas. Most probably, the one that you usually see are the wire antenna and also the reflector type antenna. So the wire antenna is the monopole antenna that is connected to your access point Wi-Fi. So you use wire antenna. Sometimes they use also microsweep antenna. And for Astro and VSAT communication, it uses reflector antenna because reflector antenna produce higher directional radiation pattern. So this is the example of wire antenna. We have a dipole, circular square, loop, and helix antenna. Other than that is Yagi-Uda antenna, which used for television broadcasting, terrestrial television broadcasting, that is placed on top of the roof. That's called Yagi-Uda antenna. For aperture antenna, is not commonly used, and you might not see it before. So it uses a metal type structure. We call it horn. So this is pyramidal horn, conical horn, and rectangular waveguides. And another type of antenna that might usually been used because of the inexpensive fabrication is the microstrip patch antennas. So it is each on top of a substrate, usually FR4 or PCB board, and this one is a copper. So the circular or square patch here is the one that radiates the electromagnetic wave. For this kind of antenna, usually they will conceal it in a plastic package so that you don't see inside. Array antennas also been used mostly for point-to-point communication. For example, Yagi-Uda antenna is what we call array because there's a director in front and a reflector, and here is a wire antenna, which is the dipole antenna. So with the director and reflector, the radiation can be directional to this direction over here, to the left side, to the right side. Other than that is a microsweep patch antenna. You have multiple patch connected to each other and radiates with that which give a high gain directional radiation patterns. Similar goes to reflector antenna. It is a high gain directional radiation pattern antenna. If you look at this is a parabolic reflector with front feed. So with this feed here, the source is over here. So the reflector reflect the electromagnetic wave and propagate to the right side. Similar goes to the parabolic reflector with Cassegrain feed and also corner reflectors. So this is uncommon, which is a bit rare, used in lens antenna because it is quite hard to fabricate and also hard to design. So with lens, for example, you have a source here. We can redirect the electromagnetic wave by using the diffraction. By using diffraction of the lens material over here. If you are using a fraction n larger than 1, you need to use this kind of concave lens, convex lens, while if it's n less than 1, you need to use the concave lens to direct the antenna to get a high gain directional radiation patterns. This is another example of a parabolic antenna, a big one. Used to communicate with the satellite in the sky. Similar for this example, this is a parabolic antenna. This is a helix antenna, usually used for point-to-point communication. might be around 5 kilometers to 10 kilometers range. They can communicate between each other. For a parabolic antenna, it can goes up to few hundred kilometers because it wants to communicate with the satellite in the sky. So that's why the parabolic antenna has a large structure. So this is the horn antenna. You have to fabricate it using metal structure. So this is a loop antenna. The shape can be circular or rectangular. So it's used for field sensing operation, requiring EMC measurement equipment. So this is a microstrip patch antenna. Mostly the research in the university use this kind of antenna to design and do the research. Students do the research. So this is an example of a dipole antenna. This is a patch antenna. So that's all for today's class. This will be the last class for this semester. So I wish you luck for your final exam. So Assalamualaikum and good afternoon.